I seriously take a break from this stuff and have so much difficulty trying to get back at it. Such a procrastinator. Big yawn. Alright, so determine a unit vector perpendicular to both vector m, which has components 5, -3, 1, and vector n, which has components 0, 2, and -4. So this is in 3 space. This is a little bit of review, so it's like a warm-up. And then once we're done that, we're going to check our answer using the dot product. So first thing is, ignore unit vector and just talk about vector perpendicular to both of these vectors. And that means that we have to do cross product, because that is the definition of cross product. So I'm going to take these two things and do the cross product. That's step 1. So 5, -3, 1, 5, -3, 1, 0, 2, -4, 0, 2, -4. And remember that if you don't like the scribble method, you can always do the formula, which requires memorizing the formula, so I highly recommend not doing it. So down to the right minus down to the left. Down to the right minus down to the left. Down to the right minus down to the left. Watch your 0 times tables. So the cross product of mn is 10, 20, 10. Now, that's the vector perpendicular to both of those, because that's the definition of the cross product. What I'm going to do now is I'm going to worry about the fact that we're looking for a unit vector. So I'm going to do that in blue. And a unit vector means that this has to be 1 unit large. So even if I reduce this, it doesn't guarantee that it's 1 unit large. So you can if you like, because you can, and I'm sure this isn't technical terminology, but you can reduce that because it is a vector. So divide by 10, divide by 10, divide by 10. And we have this, which is not 1 unit large. So I'm about to do magnitude. So the magnitude of m cross n is the square root of 1 squared plus 2 squared plus 1 squared. And I don't need brackets because there's no negatives. So that's 1 plus 4 plus 1. And thankfully, 6 is already reduced, so we don't have to worry about a reduced radical form. So if I want a unit vector perpendicular to those two vectors, the unit vector is 1 over root 6, 2 over root 6, another 1 over root 6 in component form. So if we had used 10, 20, 10 as our components in here, you would have had a reduced radical form to take place. So I got smart. Now, we have to still do the check part of it. So I'm going to change colors, and I'm going to talk about the check. And I'm going to do that in green. And unfortunately, we have to check twice. We have to check once for m, which is 5, -3, 1. And I'll do that first. And in any order, we have to take that and dot it with our brand new result. I'll leave this space for the second check. So that's 5 times 1 over root 6, so 5 over root 6, plus -3 over root 6, sorry, -3 times 2 over root 6, which is -6 over root 6, plus 1 times 1 is 1 over root 6. So we end up with 5 plus -6, which is -1, plus 1, which is 0, all common denominators, so I'm totally allowed to do that. and that's 0. So therefore, they're perpendicular, because that's what the dot product result is if the vectors are perpendicular. So now I get to do the whole thing again, because it does say check our answer. And the next one I have to double check is this one. So there's my n vector. And I should check that dot product being 0 with 1 over root 6, comma 2 over root 6, comma 1 over root 6. So it's 0 times 1, which is 0 over root 6, plus 2 times 2 is 4 over root 6, plus negative 4 times 1 is negative 4 over root 6. So that also ends up being 0 over root 6, which is equal to 0. So therefore, that checks out. So the idea that the cross product is a vector perpendicular to two other vectors is true. I have made sure that my answer is correct. And I've also, in addition, got a unit vector. All right, so I'm going to pause for a sec, and I'll come back with some properties of cross product and some suggested questions. All right, so properties of the cross product. So we've got vectors A, B, and C, and it's in R3. And K, when we run into a K, is a scalar, so it's some real number. And we've got this thing called the anti-commutative property, which means if you cross two vectors and then you cross and reverse, the difference will be that one is a negative version of the other. So we're about to prove that. And there's many ways of doing it. I'm going to do what I'm going to suggest is an easy way of doing it, even though it's not so easy. So I've only got an A vector and a B vector. So the first thing I'm going to do is I'm going to designate values for my three-space components. So I'm going to let A, and it's super, super annoying to do A1, A2, A3. So I'm going to choose to say that A is A, B, C. And I'm going to choose, that B is X, Y, Z. Then I don't have to worry about silly subscripts and stuff like that, which truly mess me up. Now, I'm not going to do the proof quite yet. I'm going to take some time to do scribbling because, to be honest, I don't have the cross product memorized. I have the system for doing the cross product memorized. So I have to do all my scribbling. So I'm going to do the scribbling in green and come back and do the proof in black. So my black writing is official. So A is A, B, C, A, B, C. And B is X, Y, Z, X, Y, Z. Scribble, 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 scribble. Down to the right, minus down to the left. Comma, down to the right, minus down to the left. Oops, typo. Down to the right, minus down to the left. So my left side, black pen, my left side, based on these vectors, is vector A cross vector B, and the resulting vector is BZ minus CY, comma, C X minus AZ, comma, AY minus BX. And now I'm going to take this space, only because I've got it, and maybe I'll be able to see everything. And now I'm going to do B cross A. So that means putting B on top. and A underneath it. Scribble, scribble, and do my cross product. So this time, down to the right, minus down to the left, comma, down to the right, minus down to the left, comma, down to the right, minus down to the left. And I'm going to change this one around only because YC is the same thing as CY, and then everything's in alphabetical order for each of the pieces. So this time, I'm going to say that the right side is equal to negative vector B cross vector A. So that means I get to write negative square bracket this stuff. CY minus BZ, comma, AZ minus CX, comma, BX minus AY. And then remembering my scalar multiplication, I'm going to take everything in here and distribute the negative into it. So this will be negative CY plus BZ, comma, negative AZ plus CX, comma, negative BX plus AY. Now if I take a look at that and compare it to the left side, it is exactly the same, but I have one more line. So I'm going to choose to put my positive piece first and my negative piece second. And now my first component is the same. My positive, then my negative. Second component is the same. Positive, negative. Third component is the same. And that means we do have left side equals right side, which also means that this anti-commutative property is for real. And there you go. All right, so I'm going to take a little pause because my hand just cramped up, and we're going to do a triple. Notice I'm not going to do these two, but I'll talk them through. Yes. Okay, so this distributed property is going to be super annoying for me. Especially since there's cross product. Ugh. So, same kind of structure. I'm going to stick with the black pen for the firm stuff, as in the stuff that I'm going to keep for real, as in the real proof. So I'm going to stick with my same structure. So vector A is A, B, C components. I'm going to say vector B is the same as we did before. So X, Y, Z components. And C, which is a new one, PQR. As long as I don't repeat, I'm okay. So, the first thing, left side. A cross B plus C. And this is going to take a lot of scribbling, and I wish my smartboard slide was a little bit bigger so that I could see everything at the same time. There's going to be some scrolling and some green stuff inserted in the middle. So, the first thing is, I'm going to have to take B and add it to C. Now, that's pretty easy. That doesn't take much scribbling. So it's X plus P, so first components, Y plus Q, second components, Z, let's do this properly, Z plus R. Now the scribbling begins. So A is A, B, C, A, B, C. And the second vector is a whole heap of stuff. So X plus P, Y plus Q, z plus r, x plus p, y plus q, z plus r. And now this is going to be difficult. I'm going to actually do it right here. So this way is bz plus br minus cy plus cq. But because I'm minusing both this and this is going to stay a negative, comma. Cx plus cp minus az minus ar, ay plus aq minus bx minus bp. Components. Yikes. All right, so now I have to match that with this side, which is a double cross product. So I'm just going to write that here before I can't see it anymore. This is the disadvantage to smartboards. Your screen runs out as opposed to paper. All right, so over here, A cross B. And I'm going to put my answer over here so I save myself some hand cramps. So BZ minus CY, comma, CX minus AZ, comma, AY minus BX. And I have to add that to, add a space, poor planning. I have to add that to A, B, C, A, B, C, cross C, PQR. That's what I designated it as. This is why your communication has to be good, otherwise the reader, me, doesn't have a clue what's going on. So BR minus CQ, CP minus AR, AQ minus BP. So all I've done, that. And now I have to take my first components and add them together, my second components and add them together, my third components and add them together, because it says add. Now, the way I've set it up was an accident, but it's actually working out to my benefit, because now I can see exactly what I have to add together right here before the comma, what I have to add right here between the commas, and what I have to add right here. So the thing is, I can also see where I'm headed, so I won't need an extra line as long as this all works out. As in, the first thing is BZ, and I do have a BZ, and I'm supposed to add on a BR apparently, and I do have that without faking any math. And then I have a minus CY, yes I do. And then I have a minus CQ, comma. Same thing here. So CX, I want that first. Then positive CP, yep, I got that. Negative AZ, even though my handwriting is terrible. Minus AR. Yes, I know I'm going downhill so I don't run into my work. And then finally, in hopes of left side equals right side, I'm going to try not to fake this last bit. So AY, yep, I got an AY. Plus AQ, yep, I got that too. So I'm not faking any math. Subtract BX, yes, I have a subtract BX. Subtract BP, yes, I have a subtract BP. So I'm sorry that my B's look like 6s. And my A or my Z's look like who knows what they look like, but I do have it worked out. So left side does equal right side. So that means that A crossed with B plus C, which is the first one I did, is exactly the same as A crossed B and then added to A cross C. Let me just double check that I wrote that first part down. Yes, I did. So the distributive property works. So this is something you can use to your advantage in other aspects of this. And usually you do this with numbers. All right, the last two things that are absolutely true about cross product, beside the fact that you've got this anti-commutative property that works and the distributive property that works, these shall remain nameless. So this is if you multiply a vector by a scalar and then cross it with another vector, that is the exact same thing as if you multiply the second vector by that same scalar and then cross it with the first vector, which is exactly the same thing as if you cross the two vectors to begin with and then after the fact multiply it by the scalar. And this doesn't have any name, but it is absolutely true. And then the last thing that's true is that if you cross a vector with itself, you will get the zero vector. So please understand that if you take a vector, let's say super ingenious 1, 2, 3, and you cross it with itself, so 1, 2, 3, if you do all the work, you will end up with the zero vector, and the zero vector is not that. That is a scalar. A zero vector is that. So this should be your result. All right, and then the suggested questions. So the next thing I'm going to do, and even though it's on the Google site as two separate entries, I'm doing it as two separate entries, but you can see it under the same thing. So it says, I think, properties of cross product and triple scalar product. So I'm about to end this and then go on with triple scalar product. So let's end.